All right, so I'll be going through an example or a non-example here of where this function here, f of x is 1 on x, is not a uniformly continuous function. Right? So I've given the definition, I've done some preparation, so here we have the definition of uniform continuity, and it's in terms of metric spaces, right? So uniform continuity is defined in many different ways, but they all have some equivalence. But here, in the context of metric spaces, we say that a function f from x to y between metric spaces is uniformly continuous if for all epsilon greater than 0, there is some delta greater than 0, such that, so here I've split off the definition into two equivalent parts, so you can end this definition here or here. And depending on whichever you find helpful, in this case, we'll find that this one is quite helpful. You can elect to choose either of them. So such that for all x in the metric space x, the function of the ball of radius delta around x is contained in the ball of radius epsilon around the function of at the point function at the point x. Right? So that's equivalent to saying that for all x and x prime in the metric space x, we have the distance in x between x and x prime being less than delta implies that the distance in y between f of x and f of x prime is less than epsilon. Right? So here we're going to go through an example where we're going to show that this function given by, so we're going from the positive real numbers, and the functions defined by f of x is 1 over x. So this is quite a classic non-example. So this function here is not uniformly continuous. Right? Okay. So what we have to do to show that it's not uniformly continuous, it would be quite tricky to use the definition as given here. So what we have to do is tweak it a little bit. So we're going to negate the conditions in this definition so that we can work to show that this function is not uniformly continuous directly from a tweaked definition. So let's do that. So when you negate for all and there exists, they just swap around. So we have there exists epsilon greater than 0, such that for all delta greater than 0, there exists, so we're going to take x and x prime. Where do they live? They live in x. Such that, so if x prime is an element of the ball of radius delta around x, or we want this to occur, and we also want this to occur as well. So f of x prime, so since we're negating the definition, or the conditions of the definition, we're saying that f of x prime is not in the ball of radius epsilon centered at f of x. Okay. So here is the negated definition. So what we want to do now is we want to satisfy this condition first, and then use our result to show this. So since we're using this line directly, so there exists an epsilon greater than 0. What we can do for some preliminary work, we could set, so I'll just start it now. So let epsilon equal, so we're going to choose a value 1. Right? And what we're going to do is, so delta can vary, right? It has to be a positive number. So you can take an arbitrary delta, positive delta value. And we're going to do this little trick where we let x equal the minimum of delta and this value 1. Right? So we're going to set x to be the minimum of delta and the value 1. So this is not very intuitive as I'm going through it now, but as we'll see, it all makes sense because we want to satisfy some inequalities, right? And it'll make sense in a minute. So we're going to set x to be the minimum of delta and 1. So what we're going to claim is that if we set x prime to equal x over 2, this is going to satisfy our condition. So let's see if it does. So let's write it like this. So if we take the distance between x and x prime, right? Because we want this to be less than delta. So if we take this distance here, well, given our choice of x prime, it's x over 2. So it's just going to equal x minus x over 2. And we can play around a bit and simplify. We get 2x minus x. And we know that x is the minimum of delta and 1. Delta is positive, 1's obviously positive. Whatever happens with delta, we know if we're taking the minimum of delta and 1, that's going to be a positive number, so we can remove these absolute value bracket bars here, x over 2. So we still don't have an inequality, but we can use the fact that since x equals the minimum of delta and 1, we're going to have that x over 2 is less than or equal to delta over 2. And delta over 2 is certainly less than delta. So indeed, we have that this implies, so what did we have? X, the distance between x and x bar is less than delta. So therefore x, or x prime, is an element of the ball, because we're working in a metric space, the ball of radius delta around the point x. Okay. And we're happy. We've satisfied this condition. We're left to satisfy this one here. So now we want to take the distance between f of x and f of x prime. So this simplifies to, so f of x, now we can work with this function here. It's 1 over x. And we make that substitution. So it's 1 over x So f of x prime is 1 over x prime. Okay, and so since x prime is x over 2, we want to get this in terms of x, so it would be 1 over x minus 2 over x. Okay, let's simplify this a bit. This is all over x. Let's write it here. Negative 1 over x. So that just makes things positive. Okay. Now, since we have that x is the minimum, again, we're using this value of x, which is the minimum of delta and 1. We have that 1 over x must be greater than or equal to 1, right? Because x is the minimum of these two, right? So 1, so whatever delta is, say if it's greater than 1, x would be 1 in that case. If it's less than 1, then x would be delta. So therefore 1 on x must be at least 1. Okay, and now you see why we've let epsilon to equal 1, because this is just an epsilon. Nice little trick. So this implies that f of x prime, so we have a greater than or equal to 1, right, or greater than or equal to epsilon. So therefore it's not contained. So f of x prime is not contained because it has to be strictly less than or less than the value. So f of x prime is not contained in the ball of radius epsilon around f of x. Okay. And that completes the proof. We've shown these two using the negated version of the definition of uniform continuity to show that this function here is not uniformly continuous.